Howdy, folks. How's everybody doing today? It's St. Patrick's Day, right? Happy Thursday. Hope you're doing all right. Let's see. So we did, just before I left on Tuesday, I found the error was my validate method wasn't returning anything. That was the last error we found. And now I think it actually works here with our, did a little tree traversal here. So we've got to talk about traversals, we'll talk about the tree, and then we'll get into the priority queue. And I think we're doing relatively well on our schedule. I don't actually need that page. Don't need Twitch Inception here. So we're just a little bit behind, but it should be okay. And we've got project 2 coming up in a week here, right? Yeah, not all of those. Just want the calendar when I click the calendar, not all my notifications. Yeah, so if it bumps into 322, not too big of a deal, but I think we can get through priority queues today. If not, just the traversals, that'll be okay. We'll talk about maps, and then search tree, sorting and selection, a little bit of ethics, final project work time. So we've got till next Thursday for project 2, and then we'll talk about project 3 will be due April 7th, and we'll start the final project probably April 5th. We'll have all of April to work on that. And then again, for presentations, I think I have an appointment at 2:30, so I think we'll plan to start at 4 p.m. instead of 3 p.m., and I think that should be fine. We don't have that many folks who need to present, so I think that'll work out okay. All right, so one of the traversals then that we're working on, and there's a pre-order traversal, there's an in-order traversal, and there's a post-order traversal. Now these ones don't really necessarily make a lot of sense yet because we haven't, like there's no real structure in our tree. There's no structure forced here. So Eric and Gary, Cynthia, and Maurice, I think, and Ruth. Oh no, I'm out of father. Oh yeah, mother's father was Frank. His mother was Susan. There we go. And now, like this order doesn't really mean a whole lot of anything, right? This is my dad's side. This is my mom's side. But if you put things into a tree in a particular order, then they'll make more sense. So don't worry too much about the traversals yet. Once we get to the search trees, those traversals will make a whole lot more sense because we can then use them to get values out of these search trees. So just kind of put those in your back pocket for now. The pre-order, the post-order, and the in-order traversals. So yeah, not too big of a deal here. So we can get these out. So the in-order, then, let's do an in-order traversal. So it goes in a slightly different order here. So it's going to go, we want to do the left child first, and then ourself, and then the right child. So the first thing we want to do, we want to, hey, Uncle Bill, thanks for coming along. Good to see you here. Happy Thursday. We need to go to the left of this position. So we're going to call in order traversal on the left position. Or so I guess we can say if my tree dot left of the position is not none, then we'll do a in order traversal of the tree and the tree dot left of the position. Then we'll print ourself, right? And then we'll do the right. Hey, Trumpet Man. No worries, my friend. You do what you got to do. And then we'll check the right. So what this is going to do, right, if we kind of imagine a tree, it's going to go, if I can draw this, oops. My Windows key has not been working very well. It's really obnoxious. I did find out my laptop is 3 years and a month old though, so definitely due for a replacement. I'm trying to decide whether or not I want to get like a nice desktop for at home, and then I can generally use the computer station. The only thing is they don't have OBS, so it would be difficult to stream from in person in the classroom. So I have options, but I don't know. We'll see. So if we had this tree again here, right, and had our generations out here. The actual values don't matter, but if we go left, self, and right, then starting from here, we go to our left, we go to our left. There is no left, so then we would do this node. So let's just number them. 1, 2, 3, 4, 5, 6, 7. We would end up with 4 first, and then 4 would come back here, and then we would do the 2, because that's the center. Then we do the right here, was 5. Then we come back, we do 1, and then we'd go to the right, and the first thing it does is go left here, so we get the 6, come back to the 3, it goes to the right and does the 7. So this order here looks really crazy, and what we'll call an in-order traversal here. But it should still print them out. So I think we can do in-order traversal of the tree.root, the position. You know, maybe we should leave that as none here too. We can default that to none. That might be a little nicer here. We'll default those to none. Equals none. And if the position is none, we'll say a position is equal to tree.root. That way, the calling the main function here is a little cleaner here. You don't have to tell it, hey, start at the root, please. But you can start from any position if you want. This will be a preorder, which is the self, left, right. And then the post in order is left, self, right. Okay, we'll see if we get that out. So Eric and Gary, Cynthia, and Maurice, and Ruth, and Frank, and Susan. All right, so notice going left first, right, we'll get my grandfather first, then we'll get my father, then we'll get my grandmother, then we'll get me. Right, and then we go to the left, so my mother's father, then my mother, then my mother's mother. Again, it doesn't make a lot of sense yet with that the structure that we have here. And then the last one is the post-order traversal. So same idea here, tree position is none. Oops, sorry, that's we're not doing Java, we're doing Python here. And we'll start off null here, and then I'm gonna just copy this one. So with a post order, we do the children first, and then we do ours. Right? So do the children first and then come back here. So with a post order, if we are going to do, this is really left, right, self. So left, we would get 4. It has no left, it has no right. So we come back here, it would go to the right first, we get to 5. Then we come back, and then we would do self as 2. We come back to the 1, we'd have to do then the right branch. The right says left, right, so we get 6. Has no left or right, it goes back here, goes to the right branch, to 7, comes back here. Now we do self, and then we do self of 1. So that's the post order, so it's like going down to the lowest generation first and then working its way back up. Is the, oh, sorry, I didn't actually run the post order traversal, did we? We'd want to do a post order, which is left, right, self, instead of self, left, right. Okay, and a post order traversal. And all those should work here. See if that goes. Oops, type in the right spot here. Eric. We'll just do some initials here, keep this faster. Right, so grandparents, father, great-grandparents, grandparents, mother, then me. Sort of a weird way to do that here. Then there's another way to do a traversal here, which is a breadth first traversal. Breadth, is there a D in there? I forget, breadth first. Given a tree and a position of none. And this is the last one we're going to look at here. So again, if the position's none, we'll start at root. First traversal. Does that look right? Okay, so now what this one does is it wants to do every generation at a time. So we're going to do all of the level 0, all of level 1, and then all of level 2. Well, to do that then, we need to grab the first item and then add all of its children to a queue for us to process, which is kind of fun. So we're actually going to make a queue that gets passed around here. So we have our queue is none, and if queue is none, then queue equals, we can just do a list here. It doesn't actually need to be a queue. A queue would perform better for us, but we're just going to take advantage of this list idea here. If the queue is none, great. So what we're going to do is we're going to process ourself, right? So we're going to print the position.data, and then for child in our position, we're going to add that child to the queue. So we're going to take our queue and we're going to append the child. Then we're going to recurse on what's in the queue. So this one gets a little bit funky here. So yeah, we print ourself, add all the children, and then we'll go run this for the new location. I think that ought to do it. Or no, so we need to, we print ourselves, we add the children, and we go to the next one. So then I think then what we're going to do, so then we're going to do a breadth first traversal on my queue.pop of 0. Grab the first thing there. Okay, grab the front of the queue. We'll go and process it, which means we'll print it, and we'll grab all the children, and it'll do the next thing in the queue, and the next thing in the queue. I think we need to then also make sure if it's not empty, length, the queue does not equal 0. So like if we're trying to do this from memory instead of copying out of the book again. So if it's not 0, let's go in and do it here. We'll go process the queue. And that should give us every item. Let's see if that one does it here. So we'll do a breadth first traversal. First is each level at a time. Should be the breadth first traversal. Let's see if we can run that one. Let's do some initials here. Oh no, it crashed. Okay, yeah, we messed it up here. Position has no attribute root. What did we do wrong here? Tree, root, we're going to append child. Oh, yeah, we need to call breadth first on the tree, position, and the queue. There we go. So give it the position is the first part, give it the queue that we're working with, and the tree here. Okay, that's what that was. Let's try that one more time. All right, so each level then is me, my parents, and my grandparents. Look at that, it worked. So again, this one will work very nicely with any given tree. It doesn't have to be a binary tree. Same with our post-order traversal and our pre-order traversal. The in-order traversal, we're having to specifically call left and then right. This one is difficult to do because it only works with the binary tree, essentially. With an n tree, you have to either do the children first or the element itself first. And the post order is a depth first, right? It's going to go down all the children as deep as it gets first. Then it'll work its way back up. So it's sort of as a depth first traversal versus the pre-order, which is going to process the elements themselves. So you might see some of these terms referenced in terms of traversals. Okay. Is that better? Make those yellow lines go away. All right, so that's some basic tree traversals. Okay, now the next thing we want to talk about is some properties of trees. here. So let's look at another tree without all the drawings here. So right, each tree has levels, right? So this is level 0 or height of 0, level 1. And we'll look specifically at binary trees here again. And level 2. So there's a couple more definitions. So there is a full tree or a complete tree. What a complete tree means, so for complete, that it is full to everything but the last level. That's an F there, not an E. Full to everything. That's an E there, right? I can't even write. That's okay. So it's full everything but the last level, and then the last level has everything as far left as possible. So this would be a complete tree. Once we add the nodes here and here, this is a full tree. So a full tree has every level has all the children except for the last level, and none of them have children. So there's no hanging children out here. So if you added a node down here, you'd be neither full nor complete. Right? You're not full because the last level is not all leaves. Right? So everything has both children except for the very last level. So you're missing a bunch of these that don't have children, and then you're not complete. So if it was over here, it would be a complete tree because we're as far left as possible. And we would add over here, and then add over here, and then add over here, and then add over here, here. Now we can take advantage of this particular structure with a binary tree here. We can do some really cool magic. So what we can do, instead of storing these with links here, right? So if we look at this, let me add another page here. The number of elements that we store per level, right? So right, this is all powers of 2. So at a level 0 or height of 0 tree, we get 2 to the height, right? Which is 1 element. With a height of 1 tree, we get 2 to the 1, which is 2 elements at this row, right? With a height of 2, we get 2 to the 2, we get 4 elements here. So the total number of elements, right? So this is the number of elements in each level is 2 to the height. The total number of elements is 2 to the height plus 1 minus 1. So total number of elements, right, is 1 and then 3 and then 7, right? And if we were to add 8 more here, right, we'd be at 15, right? So the height of 3 is 2 to the 3 is 8 more items here. So 2 to the height, right? So height of 3 would be 2 to the 4. But 2, 4, 8, 16. 16 minus 1 is 15. Right? We have 15 total elements in the tree. So some silly math here, but again, it's based on powers of 2. So what we can do is we can say, hey, for any one of these values, if I wanted to, I could store this structure in an array-based list here. So if I had a list here with indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? I can store all those values in an array here. And because we know these are powers of 2, we can do some funny math here. So 0 is the root here. 1 and 2 are the left and right child of this one. 3 and 4 are the right and left and right child of 1. 5 and 6 are the left and right child of 2. And then 7 and 8 are the left and right child of 3. Right? 9 and 10 are the left and right child of 4. 10 and 11 are the left and right child of 5. 12 and 13 are the left and right child of 6. And 14 and 15 are the left and right child of 7. So your left child is your index times 2, right? And your right child is your index times 2 plus 1. Not quite, except for 0. That's unfortunate. Let's see. So, right, so index 7 then had a left child of 14 and a right child of 15. That's working out okay. So really what we want to do is we want to do index plus 1 times 2, and then we'll do minus 1 for the left. Is that right? No, hang on, sorry. What's the mixing that up here? So let me do the chart here. We'll just chart it out. So this is your index here, and then your left and your right. So at index 0, your left is 1, your right is 2. Oh yeah, okay, so it's just plus 1 and plus 2. That's what it is. So your index doubled times 2 plus 1, and your index doubled plus 2. Is that right? So then index 1 has a left child of 3 and a right child of 4. Index 2 has a left child of 5 and a right child of 6. Yeah, so times 2 plus 1 times 2 plus 2. Now we can also go backwards, right? So then this is 3 then, right? So 3 had a left child of, that's 7 and 8. Right, and then 4 had a child then of 9 and 10. 5 had a child of 11 and 12. 6 had 13 and 14, and 7 had, nope. I broke it. I drew something wrong here. 0 has 1 and 2. 1 has 3 and 4. 2 has 5 and 6. 3 has 7 and 8. 4 has 9 and 10. So then 5 should have 11 and 12, 13, 14, 15. Nope. My goodness, friends. We'll get to it in a second. We'll figure that out in a second. I'm trying to remember what it is here. But then to figure out your parent then, so a given index, your parent is going to be your index floor divided by 2. Is that floor divided by 2? So if we were at, let's see, so this is index 0 and 1 and 2 and 3 and 4 and 5 and 6, 7, 8, 9, 10, 11, 12, 13, 14. I can't count, friends. 14 should be my highest index. That's why I'm messing up here. There is no 15. Yeah, okay, so this is good, because there is no 15. We have 15 items total. So this one is level 0, or height 0. These ones are height 1, height 1. This is height 2, height 2, height 2, and height 2. And then all of these children here are going to be the third height. Okay. All right, good. So now then we want to take to find our parent, then 0 is a special case here because it has no parent, because it's the root here. But everything else then, we want to do the opposite here. So we want to take our index divided by 2. So 13 divided by 2, right, is going to be 6.5, but with integer division, go down to 6, or the right child divided by 2. So I think actually let's do index plus 1 divided by 2. So then 1 and 2 become 2 and 3 divided by 2 divided by 2, right? Gets me 1 and 1. Then we subtract 1. Let's chart it out here again. Let's make some more room for a chart. So for 0 doesn't matter, but for 1 and 2, then we need the parent. So this is the index and the parent. So we need to get 0 and 0, and then for 3 and 4, we need to get 1 and 1. So if we add to the index, and then divide by 2, then subtract 1. Does that work? So 3 and 4 divided by 2 is, no, I'm sorry, 4 and 5. It's going to be 2 and 2.5. Integer division is 2, and then minus 1 gives us 1 and 1. Checking out okay so far. So index is 13 and 14 would be 14 and 15 divided by 2 would be 7 and 7. Minus 1 gives me 6, minus 1 gives me 6, and I point back to 6. A little ugly here, but we got there. We got there with the math. So then we can write a array-based tree, not a linked-based tree here. So we don't need positions if we wanted. So we could still be a binary tree, but we could be an array-based tree, and we could calculate all of the proper arithmetic, right? What position we need to be in just with our array. Right? So we can figure out our left, we can figure out our right, we can figure out our sibling, we can figure out the children. I think we could even do the parent, right? We had a parent. Yeah, we could do a parent of a position as well. And we can do it with just arithmetic, which is pretty cool. So if we write another class here then, let's make our class for an array-based tree given a binary tree. We need to do all of these things here, right, that we had to do with the other one. So we don't need to use nodes because we just have the arithmetic. The position doesn't need to reference a node, it just needs to know what container it belongs to. So we have this position, yeah, up above. We could get the element equals and not equals, it's fine. So then for left, right, and sibling, let's see, we can still do all of these ones here, and child. Did we do parent? We didn't do parent yet. Did we do parent down below? I think we did parent in this one, right? Yeah, we did the parent here. Okay, good. So let's implement all of these ones here. Hector, my friend, thank you so much for dropping on by and donating those bits to the Student Scholarship Fund over at the University of Michigan Dearborn College of Engineering and Computer Science. Yesterday was Giving Blue Day. I finally got the website to work, which is pretty embarrassing for U of M that their website crashed, but I guess good that lots of people wanted to give money. So finally got through like 11:30 p.m. last night and donated $50 ahead of Twitch paying me out because I know it's going to happen because you folks are so generous. So we go grab all these here. And we'll essentially start editing them for our tree here, our array-based tree. Now we don't need node, right, because there's no concept of node. Position needs to know the container it belongs to, and it needs to know its index. That's really the only thing we care about, is what index this position is. Index. It has the data, and then if it equals, so other.index is self.index, so we are the same index value, right? And we're both positions will match here. Okay. For validating, right, our container is the same, and then this is now if our index is equal to -1, will be invalid. You can't be at a -1 index. Okay. Then really we don't. I guess we can get the index back out. We can just return the position.index. Right. And then to make a position, we don't have a node here, we have an index. If index what? Does not equal -1, index. So if our index isn't -1, we can make a position out of this here. Again, we don't need a root node. I guess we can, yeah, we can start it as none. That should be fine. The length is here is fine. Make position. Now we don't have a node though. So what do we have here? To get root back out, I guess we're going to give them the position. So this should be index 0 then. Here. And then parent. Now we don't have nodes, but we need to validate. So we'll get an index. Is that, and then our parent is make position. Remember we said the arithmetic for the parent node was going to be the index, what do we write down here? +1, and that in parentheses, right? Force the order of operations here. This one's as important. Integer division by 2, -1. So if the index is 0, we'd get 1 floor divided by 2, 0, no remainder, -1 would give me -1, it'd be invalid, we'll get none back. All the other parents should work great. Right? Again, for the left then, so the left here we said that arithmetic was the index. So to get your left child was your index times 2 plus 1. Index times 2 plus 1. Should probably space some of this stuff out here. That's looking a little ugly. There we go. For the right then, right, it was index times 2 plus 2. For the number of children then, if the left of my position does not equal -1, then we'll add a child, right? Because our -1 here was going to be the invalid value, right? If we don't have one, let's see. So the left of the position, make position of the index. Oh, the other thing it has to check then is making sure that's a valid value as well, because it could be none, right? So if index is not equal to -1 and index is less than self.size. Right? Both of these need to be true. You have to be less than the size to have that valid index. Right? So then we need a place to actually store all the data as well. So then we have the self.data that we're storing here equals a list. There we go. So yeah, we don't need to track root. There we go. We don't need to track root. So root will make a position of 0, right? If index 0 is less than the size, if the size is 0, we're going to give back none. We have no root here. Okay, number of children, so then adding a root. So if we already have a value here then, so if our self.data, the length of self.data does not equal 0, where's a value error. Otherwise, set the size, and then we're going to add a root here. So we need to add self.data. Self.data. We need to append the data. And we'll make a position of the root. So to add something to the left here, then we need to make sure we have enough room for these. This is where it gets kind of funky here. We need room to add it here as we go. Let's see. So we'll validate, get the index out. And then if the index is not none, index is not, when we validate, yeah, we'll get the index out. If the index is not equal to -1, it's valid. So if it does equal -1, we'll have a value error, right? That was invalid here. Oh, that was if it already had a left. Nope, we're doing the wrong thing here. So if we already have a left. So we need to check to make sure that, so if we're going to add something to the left, that we don't already have a current left value. So we want the, what do we want to validate? So if self dot left of the position is not none, because left will give us the index and make position then will give us none if there's no position. So if it's not none, I'm going to raise the value error. You can't actually add it here. Otherwise, then we can go and add it here. This will be valid. And we want to go add this. We're going to take our self.data at the index of the self.validate, self.left of the position equals the data. We can go add it at the location, and then we'll return the position pointed at that index again. Oh my goodness. We have to give them position of an index. I guess we should probably save that index then, right? Where that should go. Don't need the node. So let's take the left index is self-validate position. You can set it there, then we can make a position out of that index. Right, same with right, but we'll do it with the right. Right of the position, right index. Set the right index. No, that didn't copy right. The right index and the right index. Right, replace. So now it is, this is our index then. Validate the position, and we're going to take our self.data at the index. I'm sorry, that's the old data, right? So old data is self.data at the index. We set it to the new one and replace the new one. Deleting gets trickier here. So we're going to skip deletes because that's obnoxious right now. We don't want to bother. Okay, we'll get to that after. Now what's missing though is, can I set values at given indexes here? Right, because my data is only ever empty. The only place we ever append is when we add a root here. So what we need to do then is we need to make sure we have space for our tree here. So if there's not room, we need to go and make some room here. So self left, right, we'll validate the position. When we validate, we'll return an index. And then when we make a position, we'll find out whether or not it's invalid. Otherwise, we'll return a none. So if we don't have room here to make that position, right, so when we go to add something, we need to make sure there's room to add it. So if we're going to add something to the left, then we need to see if we have room. So we need to see if the length of self-data is, here actually, yeah, before we go and validate it, right, because validate won't give us a good one if it's no good. So let's actually make this as a helper function. We'll do self dot check or ensure capacity. Right, we've done a similar thing when we worked with our lists here, right? Where we said, hey, let's make sure we have enough room to add more values. So for check capacity, or ensure capacity, this is when we have to do copying over our list here. So we have if the length of self.data, if that is less than, right, because anytime we need to put something down in the next level, we need to essentially double, right? So as we're going in our size with our trees here, right, we had 1 item, and then we had 3 items, we had 7 items, we had 16 items, so we want that internal storage to be twice as much. We want to have 2, or I guess we could, is that doubling and add 1, doubling and add 1, double and add 1, right? Double and then add 1, double and add 1, double and add 1. So if the length of our data, as we're trying to add something here, is, so if we have 15 items, and we don't have room, trying to remember exactly how we want to do this. So the less is less than, what do we want here? The self dot size times 2, maybe? I think if we don't have room to double, right, plus 1, that's what we were saying. So we need room to double plus 1. Then we can go and copy over self.data. So then we can say new data equals an array, and then for data in self.data, or index, right? So for index in range, length of self.data, we'll copy things over. We'll say new data at the index is equal to the self.data at the index, copy things over, so we have room. And then when we're done, then our self.data can equal the new data. right? Just to make room to put more things in. Right, as we're going to try and add a second level. So if we were going to add a child and our size was 1, there wouldn't be room. But if we would double and add 1, right? The length of self data is less than, yeah. That ought to work here. So we can try it. So we should be able to use this tree here then. Where do we go and do all that? Yeah, so this was tree. So instead of a linked binary tree, all these should still work with adding left, adding right, right, of a given position. Here, get positions back out. If we did a array-based tree. Let's see if they work. Let's give it a run. Oh, goodness. Oh, that's right. I don't have a root. It's not self-root. Let's make position of 0. Right, index 0. Try that again. E, G, okay, let's see. List index out of range. The range of length of self data? Oh, goodness, yeah, we don't, we're just appending, my goodness. That's right. We're going to append all of that here. So we'll append all the values into the array. Oh, okay, yeah. That's what we can do. None times, there we go. Now we'll have all those out there. And then we can do this like we were doing before. Instead of appending, set the index. Right, so we start ourselves with the right size with a bunch of nones, then we're good to go. We can keep on adding values. Try it again. So E and G. Gotta force that arithmetic. One more run. E and G and C and M and R and F and S. Oh, value error. Make position when we added left. If it's not none, the mother's position, add a left. Mother's position. We're trying to add left. It's not none. So we should return none. It shouldn't have had a left. So we got back something that wasn't none. And we added left. All right, well, let's put a breakpoint in. Let's check that out. So that was on adding here. We'll run in the debug mode. See what's in the list here. All right, so E, G, C. Oh, no, I didn't want to break there. Let's continue. Because that one worked. C and M and R. And now here we're going to try and add left. So this is F. We're about to add left. So if we look at our tree currently, right, so our tree has data. Oh, I didn't add. Oh, I didn't add right. So something added the wrong location. So root, we added root, make position of 0. Right, add root should have worked. So what does it think its size is? Its size is 5. We added 5. 1, 2, 3, 4, 5. Yep, so we've added 5. So size is counting right, but it's not putting the right values in. All right, so we got to stop and go back a little further then. Let's start making sure we get our values in the right location. Okay, so then in our console, we'll step. Right, what's your name? E. And then we add a root. Okay, so our tree then should have data with just E. Looking good so far. And then we're going to continue on. We'll prompt G, Let's check this one out. So let's step into our code. So we're going to add left here to the current tree. Left is none, so we're going to ensure capacity. So this should need to resize then, right? Because our length of data is less than half. We're going to make a new data, right? With room for 3 things. We will add the E, that's done. Reassign data. Okay, so we have capacity, add to our size, validate the left of our position. So the left index then. So let's see when we go left. So left of the position. So position is currently index 0. So we're going to validate the position, turn the index. So index is 0. And then we'll make position given index times 2 plus 1. Okay, so we make position. Index is 1. Is 1 less than self size? No, it's not. So that's okay. We should give them back a position here. So now our left index, let's see, left index is 1. We got the index, so then we're going to set the left index to the data in our self.data here. So it should set self-data to G. Good. And then we're going to make position of the left index. So the left index was 1. 1 is not less, so we should be able to make a position here and return that. And then we should have the father's position is index 1 of the container. Looking good so far. Right, and then mother's prompt, we get C, and we'll step through this one. So they're going to add to the right then of root and add mother. So validating self right is not none. Right will validate of the position. The position here was 0, right? We're validating the root. Give them out the index, and then we need to make position of index times 2 plus 2. So make position then of index is not -1, is index less than the length. Oh, I think we need less than or equal to self.size then, because that was probably going to be invalid. Right, now do we have a position? Adding to the right. The right index is 1. Oh, right index should, oh, we did left here. That's what it, so that says a right of the position. There we go. That was probably a typo on our copy paste. Let's see if that was it now. See if that runs. E and G, oh goodness, a value error already. If left position is not none. Oh, we need to be, no, we do need to be less than size, don't we? It's E and G and C and M and R and F and S. Okay, almost there. So then, oh, the data of the position here, that's right, is, uh-oh, where'd our data go? Position, oh, we can't get that out. The container at index. There we go. Self-container, self-index. Now we can get the data back out. Let's try that. E and G and C and M and R and F and S. Ah. The array-based tree object does not support indexing. Hey, welcome on back, Uncle Bill. Oh, that's right. So the containers, goodness gracious. Self-data. Data. A little ugly. It might work. We'll try it. E and G and C and M and R and F and S. All right. And we can traverse our trees. Whew. Using an array-based tree. Storing stuff totally different. Now, the problem with an array-based tree right, is performance on these. Now, just like a regular list, right, we're only doubling when we need to. So on average, adding stuff shouldn't be so bad, right? On average. But we can get into this ugly tree form where we are not a complete tree. If we add something and then add a right, 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 we have all of this empty space here, which is no good. Right? We don't want the empty space. Empty space is bad. So it's a problem. So it's not a great form for things that aren't kept in that full or complete form. Now, thankfully, what we got to do is we're going to take advantage of this with our priority queue. And a priority queue is a queue that has items given a priority, meaning they will be taken care of first. Like, think of like the emergency room. The most urgent case should be served first. It's not first in, first out, like a regular queue. It's whatever the priority is that we define will be first. So the easy one we just do is we just compare with less than. So you can make a priority queue that is a like sorting things by the least up goes up to the top. So we can have a min priority queue. And this is essentially going to be a array-based tree here. Now, it's going to use an array-based tree, so we probably don't want to inherit from it here. We want to keep that array-based tree as an attribute. So we're going to define init. Given self, we'll have data equals an array-based tree here. Now we have some rules. So when you add something to a minimum priority queue, we need to see where it needs to go, right? Because we want to have the smallest thing on top. So what we want to do, let's see, we have, when we're empty, right, we're just going to add to the top. Because it adds here. The next place we want to add, so we want to keep this in a complete structure here. So we're always going to add to the last level farthest left here. Then it needs to get sorted. So if we have some values here, so what we have to do is we're going to say the smallest value goes to the top. So let's actually draw this in like this. So we add like a 7. Sure, it's now the smallest value. If we wanted to add a value here, so say let's add a 5. It starts here, and then we do this process called upheaping. Upheaping says go up the heap until you are no longer less than your parent. Right? If you're less than your parent, you swap. Right? And then we'll swap 5 and 7. 5 and 7. Great, now we're done. Now we want to add, say, a 6. Sure, no problem. We're not less than our parent. We stop. Okay, now let's add another value. Let's add a 10. 10's fine. No big deal here. Let's add, say, a 4. So we add a 4. It goes to the next available position, and then it's going to upheap. Okay, well, we need to swap 4 and 7. 4 and 7. Okay, now we need to say, hey, are we less than our parent? Yes, we're less than our parent. So let's swap. 4 and 7. I'm sorry, that was a 5. 4 and 5. So as you add values, you need to upheap them so they'll end up in the correct location. So if I were to add a 3, I'm less than my parent, I need to swap. 6 and 3. 3 is less than 4, we need to swap. 3 and 4. Okay, works out okay. Now that's upheaping. Now to remove the smallest item here, we take the top here and we eject it out here. Now what we do to keep our form is we need to give it the last item. So we find the last value, put it up here, and then we do a process called downheaping. So when we downheap, we swap with our smallest child. So 4 is smaller than 5, so we're going to swap with the 4 because the smallest child needs to be above, and 6. And then we're done. We're done. We have no more children. Okay? If we were to remove the 4, right, we would put the 7 in its place, and we would say, okay, let's swap with the smallest child. Okay, so 7 and 5 swap. 5 and 7, great. 7 is less than 5. 7 is more than 10. Great, we're done. So this process just keeps continuing. So you upheap and you downheap as you add values here. So to enqueue a value here, we're going to put it at the last available position, right? Now this is sort of actually silly to try and store all of it this way here and use all of this other container stuff. So we're actually going to skip over that. Let's forget that. We're just going to use a list here. and we'll manage this ourselves. We'll do a lot of these similar things here, if that's okay with you. So when we go and add some data, right, we're going to go add it to the last available position. Maybe we do want to use that tree. Maybe it'll make sense here. Just getting the last one's going to be obnoxious. Yeah, array-based tree, that's fine, that's fine. So we want to add it to the end of the array-based tree. So we can say, hey, if we have a length in here, don't we? Oh, I can't scroll now. What happened? My Windows is freaking out here. Really got to get that new computer here. Don't we have a length? Yeah, length is returning self-size. Good. So if the length of our self data is 0, then we'll take our self data and we're going to add a root. No, okay, this is really annoying. Sorry, we can do this better. We can do it better, but just by tracking it ourselves here. So if the length of self data is 0, then we're just going to take self data and we're going to append it. No, actually, really, we're always going to append it when we add something because we want to add it to the end here, right? So we always want to go add it to the end. Then what we want to do is we want to start upheaping. So then we call self.upheap given, and now we need the index of this, so it's the length of self.data minus 1. That's where the index is here. Okay, and then for our upheap method, given an index. So if the index is 0, we're done, right? That's it. We're game over. So really, if it's not 0, we're going to start doing something. So we want to see, hey, are we less than? So if self.data at the index is less than, and now we need these same arithmetics here. So I'm going to add those same self.parent of an index, and so that'll return the index plus 1. Was that floor divided by 2 minus 1? Is that what we did for that? Index plus 1 divided by 2 minus 1. Yep. We'll get the parent index out here. And then we need a left of an index is same arithmetic for left. So that was index times 2 plus 1. Index times 2 plus 1. And then we need a right of an index is index times 2 plus 2. We can calculate the different values here. So, okay, if I'm not 0, I know I have to have a parent. Right, so if we're less than the self.data at the index of self.parent of the index. So if I'm less than my parent, then I need to swap. So if I am, then we'll swap. So we need, you can do it in one line. I hate doing it in one line. So I'll say temp is self.data at the index, and then self.data at the index becomes self.data at the parent, and then self.data at the parent becomes the temp. Then we're going to upheap again. And we're going to call self.upheap at that parent index. So I guess we should probably save the parent index, right? So then how about we have a parent index? Because we're going to use that a bunch here, and that's kind of annoying. Parent index, and then we're going to upheap the parent index. Right, we're going to recurse, call it again, see if we're greater than our parent, see if we're greater than our parent, see if we're greater than our parent. Right, keep on upheaping ourselves that direction here after we add a value. Okay, then we can dequeue, or I guess we could say like front or maybe front. right? We're going to return self.data of 0, because our front is always the top here. This might be none, and it'll just crash. We're probably not too concerned here. So this is O of 1, right? I always know where the front is here, easy. To enqueue something then, in terms of performance, right, because it has to upkeep possibly some number of times, what we're going to get here is actually logarithmic, log of n, because I'm forcing my number of elements to be in this full, complete tree structure here. Where do we go? So the most I'm ever going to have to do is the height number here, and height is logarithmically related to the total number of elements, right? Because our total elements was to the power of height, so that the height then is logarithmic to the total number of elements, right? I'm sure that's some math somewhere. So the performance then of enqueuing something is log n, which is pretty good, right? To enqueue something. For front then, and then we need to define a dequeue here, dequeue of self. Now this one will also be O of log n, because I will then take the last item and I have to downheap it possibly all the way, right? And again, a number of levels operations here. So we're going to have the data is self.data at 0. So we'll be able to return that when we're done. Then I want to take self.data at 0 and assign it the value of self.data.top. Right? Take the last thing off. Put the last thing off, put it at the top. Then we can start downheaping. So we'll call self.downheap given 0, index 0. And we're going to return data. So we can define downheap. Downheap of an index, right? If the index is less than the length of self.data, we're good to keep going, right? If the index is ever more than this, we're done, right? There's nowhere to go. So really we're saying if we're less than, we can keep on going here. We need to check to see if we should swap. So we should swap with the smallest child if it's smaller than us. Okay, so we need to find the smallest child if we have any children. This is where it gets a little funny here. So we need to check to see if we have a left child, if we have a right child, and which one is smaller. Okay, so left and right will give us indexes with no regard to whether or not they're valid here. So valid means I'm less than the length here. So if, so we're going to start with right. So we'll say if the self.right of an index is less than the length of self.data, I know I have a right child, right? Must have a right child. So then my smallest child will equal self.data at the index of, I guess we should have right index. We should do that. So we'll have a right index is self.right. And then we'll have a left index is self.left of the index. So if the right index is less than the data, then I know my smallest child must be the right unless I know otherwise. So I'll start with that one. Okay. So I might have a smallest child. I might not. So let's actually start smallest child here as none. Okay. So if I have a right, it'll be that one. Then I want to say, hey, if the left index is less than the length of self.data. So if I have a left, right, then I need to see which one's smaller. No, let's go in the other order. Sorry. So if we have a left, we'll assume left is the smallest equals the self.data at the left. Then if I have a right, let's see if then the self.data at the right index is less than the smallest child, then my smallest child must be self.data at the right index. Actually, we want smallest child. We want the index, don't we? We want the smallest child index here. Shoot. It'll just be left index. And then if the self.data right is less than the self.data at the smallest child index, then my smallest child index will be self.right, or right child, right index. So the reason is when we're doing this downheaping process, right, when we go and start downheaping a value. So if I take 5 off, here I'm going to put 10 in this place here. I need to see which one of these is smaller to swap with. If I didn't have a 6, then I only have a 7. Right? There is no right child, so we need to know the index of the smallest child if we have one. Right? So then if my smallest child is not none, if my smallest child index is not none, then we can swap. Right? We'll do this temp thing is self.data at the index, and then we'll say self.data at the index. We'll swap with the smallest child, self.data at the smallest child index, and then the self-data index at the smallest child is the temp, and then we'll call this temp, and then we'll call self.downheap on the smallest child index, right? The thing we just swapped. Is not none. So we start off at none because I might not have any children. If I don't have any children, I'm done. Right? Then we see if we have a left, it's probably the smallest. If I have a right, it might be smaller than the left. We'll have to find out. Then I know which one the smallest is. I'll swap with it and recurse. If I don't have any children, then that's it. We're done. And then we'll just recurse with the downheap. So we'll keep lowering that level by level by level until it finds that it is no longer less than its children. Okay, so for our min priority queue then, we should be able to add some values. So the only thing we have to do then when we enqueue, we just append, it just adds, right? Just keeps on adding here. And then we upheap it, right? We add to the bottom, and then we upheap it all the way up to the top, as high as it needs to go. Or if we take something out, we swap at the last, downheap it, and return. So downheap will just keep on going over and over and over until it no longer needs to swap. So let's skip all of this for a second here. We'll comment all that out. And let's do a priority queue. So we'll say for number in range, let's do 10 numbers here for fun. Let's say, we got to make our priority queue. So here's our PQ priority. Queue is a priority queue, min priority queue. Let's take our priority queue, priority queue, and we'll enqueue a random.nextInt. We got to import random, don't we? Import random. Import random. Man, there's a lot of code in this. Random.nextInt. Let's say 1 to 100 or so. Let's add a bunch of random ones. So now 2 values can be the same in a priority queue. You just can't be greater than your parent. So we'll add a bunch here, and then we'll say while the my priority queue not is empty. Is empty. Right. So we probably need a size. Define a length. We return the length. Self.data, and define it as empty, and return length of self equals 0. Okay, so when we're not empty, then we will print the priority queue.dq, dq the value, and print it. We should get them in sorted order using our priority queue here. Oh goodness, not next int. Next is a capital I int. Run. Is it capital R random? What is? Why is it not importing right? Am I losing it here? On random. Right here. Random dot rand int. Oh, it is lowercase. Oh, rand int, not next int. Dot rand int. Okay, there we go. Okay, now it is suggesting rand int. Thank you. Uh-oh, min priority queue has no upheed. It's upheap. Thank you, typos. All right, okay, it's close. So 4, 9, 45, 47, 54, 60, 76, 79, 98. Looking good so far. There's 4, 5, 6, 7, 8, 9. We didn't get the last one here yet. Pop. So after we pop it, if it's empty, we can't downheap when it's empty, right? So if we're, I guess we can check if the index is less than the length of data. So it should have been index 0 and the length should have been 0, right? When we popped out that last value. Should have been. When the data is for dequeuing. Oh, once we pop it off, it's empty. Okay, so we can't pop if it's empty. So I guess we only do this then if the length of self.data is greater than 0. Then we can pop it off. I guess we still need to pop it off, we just can't assign it. Shoot. We still want to pop it off, we only want to assign it if the length is less than 0. Let's see. Because we want to put the last thing in. How do we check to make sure we don't do that? Yes, if the length is greater than 0, it will be greater than 0. Okay, so let's just add one more check here then. So we'll do pop it off. Oh, that is data, right? Let's see. I'm going to replace it with that one when we pop. How about value is that? And then if the length self.data is greater than 0 now, then we can assign self.data at 0 equals the value and start downheaping. And return the data. Try that. All right, awesome. Our tree's not defined, oops, yet, but we get our values out. All right, oh, shoot, we're a little over time. All right, thanks, folks. It's been fun. This was priority queues. We'll play with them in lab on Tuesday, and we can go from there, okay? Take care, everybody.